Somewhere in the universe, two black holes collide. As heavy as stars, as small as cities. Literally black, the complete absence of light, holes, empty hollows. Tethered by gravity, in their final seconds together, the black holes course through thousands of revolutions about their eventual point of contact, churning up space and time until they crash and merge into one bigger black hole. An event more powerful than any since the origin of the universe, outputting more than 1 trillion times the power of 1 billion suns. The black holes collide in complete darkness. None of the energy exploding from the collision comes out as light. No telescope will ever see the event. That profusion of energy emanates from the coalescing holes in a purely gravitational form, as waves in the shape of spacetime, as gravitational waves. An astronaut floating nearby would see nothing, but the space she occupied would ring, deforming her, squeezing, then stretching. If close enough, her auditory mechanism could vibrate in response. She would hear the wave. In empty darkness, she could hear space-time ring, barring death by black hole. Gravitational waves are like sounds without a material medium. When black holes collide, they make a sound. No human has ever heard the sound of a gravitational wave. No instrument has indisputably recorded one. Traveling from the impact as fast as light to the Earth could take 1 billion years, and by the time the gravitational wave gets from the black hole collision to this planet, the din of the crash is imperceptibly faint, fainter than that, quieter than can be described with conventional superlatives. By the time the gravitational wave gets here, the ringing of space will involve relative changes in distance, the width of an atomic nucleus over a stretch comparable to the span of 3 Earths. A campaign to record the skies began a half-century ago. The Laser Interferometer Gravitational Wave Observatory, LIGO, is to date the most expensive undertaking ever funded by the National Science Foundation, NSF, an independent federal agency that supports fundamental scientific research. There are 2 LIGO observatories, one in Hanford, Washington, and the other in Livingston, Louisiana. Each machine frames 4 square kilometers. With integrated costs exceeding $1 billion and an international collaboration of hundreds of scientists and engineers, LIGO is the culmination of entire careers and decades of technological innovation. The machines were taken offline over the past few years for an upgrade to their advanced detection capabilities. Everything was replaced but the nothing, the vacuum, one of the experimentalists told me. In the meantime, calculations and computations are underway in groups across the world to leverage predictions of the universe at its noisiest. Theorists take the intervening years to design data algorithms, to build data banks, to devise methods to extract the most from the instruments. Many scientists have invested their lives in the experimental goal to measure a change in distance comparable to less than a human hair relative to 100 billion times the circumference of the world. In the hopefully plentiful years that follow a first detection, the aspiration is for Earth-based observatories to record the sounds of cataclysmic astronomical events from many directions and from varied distances. Dead stars collide and old stars explode, and the Big Bang happened. All kinds of high-impact mayhem can ring spacetime. Over the lifetime of the observatories, scientists will reconstruct a clanging, discordant score to accompany the silent movie humanity has compiled of the history of the universe from still images of the sky, a series of frozen snapshots captured over the past 400 years since Galileo first pointed a crude telescope at the sun. I follow this monumental, experimental attempt to measure subtle shifts in the shape of spacetime, in part as a scientist, hoping to make a contribution to a monolithic field, in part as a neophyte hoping to understand an unfamiliar machine, in part as a writer hoping to document the first human-procured records of bare black holes. As the global network of gravity observatories nears the final stretch of this race, it gets harder to turn attention away from the promise of discovery, although there are still those who vehemently doubt the prospects for success.